The things I think you will probably see on the exam later tonight and streaming.
Hey guys, who you two?
Okay. Question 11. Consider the following limit structure, and it's asking which of the statements below about the molecule is false. So let's look at A. And we should. There are 10 sigma bonds and 2 pi bonds. So how do we verify whether that's true or false?
You count each individual bond for the station.
Okay. So every single bond has 1 sigma bond.
That's like, I thought even the double bonds counted as one.
I was getting there. Every single bond has a sigma bond, and every double bond has a sigma bond and a pi bond, right? So if we count all the red ones, because we said our sigma is red and then our pi is blue, and we said that every single bond is composed of a sigma bond and every double bond is composed of 1 sigma bond and 1 pi bond. How many red lines and how many blue lines do we have?
Yeah, it's because it's too much.
Okay, so 10 and 2, so we have 10 sigmas and 2 pi's. So that's true. So what's false? False. Carbon 2 is sp2 hybridized with bond angles of 120. What do y'all think?
Yeah. I agree.
So we can identify, let me erase these colors right now. So we can identify the hybridization by counting how many electron regions it has, right? So we consider that double bond a whole electron region. So that's 1, 2, and 3. So S, P, P. So therefore it's sp2 hybridized for sure. That checks off the first part of the answer choice B. So that's right. Now we know that things that are sp2 hybridized have bond angles of what? 120. And that's just something that we have to know, right? It's not, you're not gonna get one of those things in physics lab and start calculating the angles, because the angles in this are not 120, but it's implied because it's sp2 hybridized that it is 120. It's just not shown. All right. So B is true. What about C? Oxygen is sp3 hybridized. So again, we count the electron regions. So we count this as 1, this as the second one, and this as a third one. So we can clearly see that oxygen is not sp3 hybridized, it's sp2 hybridized.
You just add those numbers.
Yeah, I just added them because they're implied, they're not shown, but they're implied. So sp3 or sp2 hybridized for the oxygen, meaning that statement is false. And you could, if C was true, if it had said sp2 hybridized, we would have to go through the rest on a test, right? But for time's sake, we're going to move on. All right, the hybridization of the central atom in aluminum bromide is what? So we know Al Br3. I'll draw my little pairs for everyone. And is that the correct structure, or does aluminum have a lone pair on it? The one before? And why is that? Yeah. Can you say it louder, Rami?
Efficient.
An efficient?
Efficient.
Efficient, meaning it's it goes by the sextet, whatever that means, and it accommodates 6 electrons in its valence shell.
It's a deficient.
Boron as well, and then hydrogen also has a deficient octet. Its octet is a duet. That only, or it's not, its full valence is a duet, not an octet. Which atoms they're forming with?
So it's like, it goes,
It was like, if it was like AlCl3, Yeah,
So if it's boron or aluminum with halogens only. Yeah, we should. That was correct.
yeah.
Halogen.
You'll see like, it's gonna be with halogens and stuff is the way you're gonna see it.
But they can be.
Alright, so it's clearly. Alright. So we said because it has 3 electron regions, what is it? What is its hybridization? Do we all agree it's sp2, right? That's just how we identify hybridization. We look at the amount of electron regions, 1, 2, 3. S, P, P, we used 1 S and 2 P's, sp2 hybridized. So we'll go for answer choice B. Yeah.
Someone asked if there's sound. Someone asked, is it just me or is there no sound?
Is it just them though? Everyone else on Zoom, can y'all hear us or? Oh, that's.
Turn up the volume.
I can hear you.
Okay, perfect. Thank you.
There's a streamer.
This is streamer.
Streamer pod.
Okay.
No distraction.
All right. Which of the following inequalities accurately describe the relationship between 2 ionic species in terms of size? John, why are you not in class, man?
He's in the wreck. Bro, falling up while listening.
All right.
I said we go pull up on John and put 5 to 5.
Oh,
For the test.
all right. I'm gonna stop sharing my screen because I'm gonna go grab a periodic table so we can use it.
Oh, cheers. Y'all are bullies, bro. Come on, we gotta get out of here. At least I don't get her intro.
Like who you call plus bullies and then he's just winning.
That's what like biology, biochemistry, that's what you say. So you guys should start making some files.
I'd be interested, I'd watch.
I'd watch a day in the, I'd watch a day in the reliable
Like,
version.
even do any editing, huh?
You don't need to.
Now we're gonna be late on purpose to our session. Okay, let me start sharing
You're
again.
late because you're editing, that's fine.
Okay, I'm sharing my screen. Okay. All right. So which of the following inequalities describes the relationship between two ionic species in terms of size? So we're looking at ionic gradients. Alright, so arsenic 3- is going to have krypton configuration, and yttrium 3+ is also going to have krypton configuration. And this might be select all that apply. Okay. So if we're looking, do we all agree that arsenic 3- and yttrium 3+ are, they both have the same amount of valence electrons?
Yes.
Because arsenic is right here. So when it gains 3 electrons, it's going to gain 1 there. It's going to be in that configuration. And then if it gains another, it's going to be in this configuration. And if it gains 1 more, that's 3-, it's going to have the same configuration as krypton. We all agree on that. Okay. So what about yttrium? Yttrium's down here. When it loses its first electron, it's going to come from the S subshell first. And then the second electron is going to come from the second electron in the S subshell. And then it's going to lose its electron in the D subshell. So it's going to lose all these 3 electrons. So it's going to pop all the way back over here to krypton configuration as well. Do we agree on that? So they both have the same amount of valence electrons. Now, which one's going to be larger? The one that has the greater nuclear charge or the smaller nuclear charge, aka more protons, or the one that has less protons? And typically anions, if there are isoelectronic species, as these 2 are, anions are gonna have a larger radius because you have more electron repulsion happening, right? Whereas when you're losing these electrons, you're gonna have less electron repulsion happening. So it's gonna cause it to be smaller. So we would expect arsenic 3 minus to have a greater radius than yttrium 3 plus, right? Is that what this says?
Yes.
Okay, so that's an answer. And let's look at the other two. Lithium plus and acetine. So AT is going to be down here. And lithium is all the way over here. So when lithium loses an electron, it's going to have helium configuration. And then when acetine gains an electron, it's going to have radon configuration. Which one is bigger? Is going to be larger, radon or helium? Radon, because it's further down on the periodic table, meaning it has a lot more energy levels stacked on top of each other, and you can kind of just think of them as layers of something, like an onion. The more layers you have around the onion, the bigger the onion's going to get. So we can see that lithium plus is going to be much smaller than radon or than acetine with the -1 charge. But answer choice B says that lithium plus is larger than acetine, so that's wrong. So that makes sense for everyone. You're definitely gonna get something about atomic or ionic radius. So if you don't understand that idea, now is the time to ask a question before we keep going.
The same thing, right?
Not necessarily. Atomic radius assumes just all atoms, whereas ionic is you're having your ions. So like these are ions. Atomic radius just follows the trend of as you go from left to right, you decrease size, and as you go from top to bottom, you increase size. That's the trend for atomic radius. There's not really like anything you got to be on the lookout for. All right. So let's go ahead and check this one out. What about C? Is calcium 2 plus going to be bigger or smaller than iodide? Yeah, so calcium 2 plus, it loses two electrons, right? So it's gonna lose this one first to have this configuration, and then this one after to have argon configuration. So this is where we are with that. So we're right there. Iodide is going to gain an electron to become iodide, and it's going to have xenon configuration. Which one's going to be bigger? Yes, well, iodide, right? Because it has xenon configuration. Therefore, we should expect I minus to be bigger than Ca2 plus, but that's not what this says. So that's wrong. And then selenium or selenide, see where that is.
One down right from phosphorus.
Yeah, I saw that. Wait, one down from phosphorus.
Down right.
Oh, okay. So selenium is going to have a charge of, in this specific thing, it has a charge of 2 minus, which means it's going to have which atom's configuration if it gains 2 electrons from this point. 1, 2, yeah, krypton configuration. So we can highlight, that's where selenium is going to be. Phosphorus 3 minus is going to be right here. It's going to be 1, 2, and 3. It's going to have argon configuration. So this one is for Se2 minus. This one is for which one's going to be larger? Se2 minus, right? And that's exactly what it says. So answer choice A and D are both correct. So I wanted to change this one a little bit. So determine which of the following hydrogen atom transitions has the longest wavelength and which has the shortest wavelength. Select 2 options. one for the shortest. It's bigger because it's closer to the noble gas. No, it's bigger because as you go down the periodic table, atomic radius increases, right? So looking for this. Yeah, there is. It's in the group me. I sent it on Tuesday. Around 6 a.m. So you can go run through that. All right. So which one is going to have the longest wavelength? What? I heard someone say it. I mean, I heard someone say something, but I couldn't hear it because I listened to music too loud.
Should I go to the lowest energy levels?
Okay, that's a good guess. Anyone else?
The energy difference, is this the difference in range, or like?
Did you meant to put 8 to 3 or is it 8 to 4?
8 to 3. I changed it 8 to 4 to 8 to 3. So we can see that maybe we can do a refresher about our hydrogen transition series. There's 3 that you need to know that are going to help you solve these problems without having to do the Rydberg equation for each answer choice. The first one is Lyman. And it's when the final n value, so n final is equal to 1, and it emits a photon in the, which y'all remember what region that one? UV. So UV. The second series is Balmer. Final n value is what? 2, and then it emits a photon in the visible light region. And last one is Passion. Final n value is what? 3. Emits a photon in what region? Yeah, so IR, infrared. So what we know from our very great professors here, I should say, right? That IR is lower in energy than visible, which is lower in energy than ultraviolet, right? And we know from another equation that energy is inversely proportional to wavelength. So the higher the energy, the smaller the wavelength, right? So which out of the 3 of these, which one's going to have the highest, longest wavelength? What? Out of the 3 of these? Infrared, yes. It's on the right side of the visibles.
So it goes UV, visible, infrared?
Yeah.
I thought it was UV, infrared. visible.
No.
Yeah, it's like, you can remember it because like ultraviolet, it's like a violet,
Yeah.
and then infrared. 'cause it's
Below
after
red.
red.
Yes.
All right, so we expect the longest wavelength to be the one with the n final is 3 because that's infrared, so it would be longest lambda. And the shortest one would be which one?
That's the highest. No, yes, it's the lowest.
UV, right? Because it's gonna have the highest energy. And we know that from this equation that energy and wavelength are inversely proportional. So the greatest energy has the shortest wavelength. So shortest lambda. So from this, we can deduce which one's gonna have the greatest or the longest wavelength and the shortest wavelength. So let's start with the longest wavelength. We're looking for something that is a Paschen series transition, so it's going to final n value is 3, and that's either these 2, right? So here was
Well, went down to those 2.
okay.
You're like in the JPO.
So with that, which one do you think is gonna have a higher or longer wavelength?
It'd be 8 to 3.
Yeah. Why do you say that?
Because it's a smaller jump, meaning that there's less energy being input to create it.
Exactly. So the answer choice for the longest is going to be this one. Even though they're both n final equals 3, they're both Paschen series, so they're both IR. The one that has the smaller jump means it's going to release the least amount of energy, meaning it's going to have the longest wavelength. So, and then which one would be the shortest wavelength? D, exactly, because it's a Lyman series transition, right? So it's going to release a photon in the ultraviolet region, which we know is going to have the highest energy and the shortest wavelength. So make sure y'all know those.
But you said 2 to 1.
Yeah,
That's 48.
so what it was, I'm saying between the smaller energy.
What if it was-
It's the same thing, man.
Or where?
I just,
Never
yeah,
had the shortest.
I flipped it because,
You know, but on the peer review, bigger,
The more energy.
yeah, no, I just changed one number. Yeah,
But that's visible.
yeah, you know,
That final end.
Oh, never mind. Wait, so I am still confused about why 8 to 3 is it conserves more energy than 12 to 3.
it's not, what makes you say it's conserving energy?
Well, because I honestly don't know what the numbers stand for. I guess it's why.
It's the amount of energy levels it's going through. So you can kind of think, have you taken a physics class?
I didn't do well in it. That's why I'm a biology.
All right, anyways. What's gonna hurt more? You jumping off a 5-story building or a 9-story building? Or a 12-story building, sorry. 5-story building or a 12-story building, which one's gonna hurt?
Which is better, more than 12.
Yeah, so you think of the 12 as having the higher energy.
Yeah, you're starting from a even higher energy level, so you're gonna hit the ground with more energy.
So you're saying 12 does have a higher.
Because
Yeah,
it's
yeah,
still-
it's gonna release a photon with higher energy, meaning shorter wavelength.
Oh, I understand. Okay, that makes sense. Thank you.
Yeah,
I don't know why that clicks, but it is.
hey man, as long as it clicks. Okay, what is the molecular geometry of SF6? Should be off the dome really quick if you memorize that.
You bring up the graph.
There's no graph needed for this.
That's the
It's like neutral, right?
Yeah.
Yeah, good job, John. So if anything, if a central atom is bonded to 6 atoms, off the dome, you should be like octahedral, okay? There's no needed to draw the Lewis structures, calculate valence electrons, add lone pairs. There's no, it's not necessary for this problem. You'll just waste your time. Yeah, what's up?
Are you gonna like just on the difference between molecular geometry and electron geometry?
Yeah, most definitely.
Bro, you want
So wouldn't we have to write it to know?
It would be an answer choice. So it would be like, what is the electron geometry of this compound? And you give you multiple answer choices.
So they didn't even specify that there's a difference. So it's like my whole class just thinks this molecular geometry. But I try to explain to people I sat next to like electron geometry, like geometry difference, they're like,
I told them to come to our sessions.
they already know for me though, so money's up.
I bet. I'll look at their test quick.
You'll see the average for Sadegis and look at that question. You'll see probably everybody missed it.
Speaking of the difference between electron geometry and molecular geometry. You wanna explain that, Daniel?
Yes. So electron geometry.
Sorry. Say it loud for the people on Zoom, and Rami, can you just, it's gonna say something.
The question is, does this compound have the same electron geometry as it does molecular geometry? And that is depending on the lone pairs.
Okay, so let's draw this one out. So we have XeF4. Xenon. Bonded to 4 fluorines. And what's that trick that we said to calculate how many central atoms are on the, or how many lone pairs are on the central atom?
4 times 8.
So we have, well, I guess first we should calculate the amount of valence electrons. So we know each fluorine brings 7 electrons to the table, and we have 4 of those. So it's gonna be 7 times 4, which is 28. plus the 8 that xenon brings. So it's gonna be 36. And we know that each terminal atom needs 8 valence electrons. So it's gonna be 8 times 4 equals 32. So we know that we're gonna have 36 minus 32. We have 4 electrons on the central atom, which means we have 2 lone pairs. So if you don't recall that trick that we went over a couple weeks ago, you can probably find it in a YouTube video. But essentially, what we did was we found our valence electrons, and we were saying how many lone pairs are on the central atom. And we said there's a trick for that. You just multiply the number, you multiply 8 times the number of terminal atoms. So you have 4 terminal atoms, those are the 4 fluorines. Multiply them by 8 gives us 32. Do 36 minus 32, we have 4 extra. Those go onto the central atom. So we know, let's identify now the electron geometry, EG, and the molecular geometry. What is the molecular or electron geometry first? Okay, octahedral, exactly, because we know that it has 6 electron regions around it. So this would be 1, 2, 3, 4, 5, 6. We know that that means it has electron geometry of octahedral. So. Okay. What about the molecular geometry, Daniel? Without looking at that note.
Square planar.
Square planar. Do we all agree with Daniel?
Yes.
All of us?
Yeah.
Okay, perfect. Square.
Barely memorized them today.
So, yeah, with that,
So how did you figure out it was square planar?
just memorization of the whole table. I can show you that table. This table, not this table, this table. So every time, if it's octahedral electron geometry, and you add 2 lone pairs to it, you go to this section in square planar.
Okay, so for electron geometry, it doesn't matter for where like, or how many lone pairs and bonds there are, it's just like how many groups there are.
Yeah, exactly.
And in geometry, it does matter whether
Take
it's
into
lone pair.
consideration the repulsion of the lone pairs, and then that's why it's different from the electron geometry.
Thank you.
Yeah. Okay, so clearly this is false. They are not the same. And we thought, how many sigma and pi bonds are present in the following? You're gonna get something like this. I'm pretty sure I've seen it the last 3 semesters. This might be a silly question, but there's an easy way to memorize the molecular geometries.
At this point, not really.
Yeah, I don't know. I told all like the students that come to our sessions to start memorizing them like weeks ago, because it's something that takes a little bit of time to, put into your brain. So the best thing you can do this late is probably just make some flashcards right before the exam and just keep reviewing them up until that point. Maybe Rich has something to say about that.
Honestly, I just stared at it enough times. I stared at it enough times till I knew what was going on. This is what I did.
The last thing I looked at was that night and the first thing I woke up to in the morning.
All right. So yeah, I'm sorry. Maybe you can
The last thing I looked at.
try to figure it out.
The first thing I looked at.
And also knowing how to draw.
I did that
the
yesterday.
kind of like
Square
tell.
Unfortunately not,
Oh, yeah,
but
for
I
sure.
have it memorized, so it doesn't matter.
Down, like literally make the shape.
Whenever it's like this way,
For sure.
linear, trigonoplanar,
Yeah.
tetrahedral.
How many sigma and pi bonds
Linear,
are present in the following compound?
So it's like these two are invisible, but if you.
So they drew it in a kind of a condensed way. They didn't show you that these branched out, but you can draw that yourself.
It's like,
On your exam, we'll probably draw it like out completely.
Yeah.
Because he doesn't should have E on it. Or is the answer to it? So he that we don't see. But like you had.
All right. So single bonds have a sigma bond. right?
You think you're cute, huh?
And we know that every type of bond has one sigma bond. So whether it's a single bond, a double bond, or a triple bond, they all have at least, they all have one sigma bond, right? So let's highlight one of each, or one from each section. Okay, and we know that double bonds are composed of a sigma bond and a pi bond. Triple bonds are composed of a sigma bond and two pi bonds. So we know that this double bond has one sigma bond, that red one, and that blue one is the pi bond. How many sigma bonds, how many pi bonds? And look at the answer choices. And cross out B, C, and D really quickly. E, wait. So yeah, all you're doing is counting the amount of red lines. 4, 5, 6, 7, 8, 9, 10, 11. The answer choice would be E.
Energy. What's on here that everything is really good? I don't do that yesterday, my damn laptop.
I'm not asking about this guy.
You didn't carry the team?
Although
Huh?
he sent out
You didn't carry the team.
Well, that's why I took it forever.
I did all
Right.
that.
Any questions on that?
not on that one, but this one's like way further down. But how do we determine the valence electron for iridium? That's a transition metal.
Iridium?
Yeah, that was one of the questions. It was question 30.
You can count.
Question 30.
Yeah, for valence electron. How do you?
To make graphs and
Yeah.
Yeah, so
Let's count
the
valence.
valence electrons are the previous S subshell electron for transition metals.
The highest orbital plus unfilled, right?
Yeah, so it's the previous S subshell plus everything in the D subshell. So what I mean by that, maybe we have stuff up here on table here. Yeah, that's crazy.
That's great.
That is crazy.
Let's turn it on.
Had enough.
It's not loading.
That is great.
Would you use the F subshell as well, because there's one right before the D subshell irradiance in? Or do you just ignore the F subshell?
Sorry, Rami, I'm because I'm trying to figure something out.
Okay.
For sure.
So sigmas are horizontal and pi's are linear. So I think
H only has. There's no way that pi does.
All right, 1 second, I'm just grabbing up here on table.
yeah, that's why that was. I care enough. Especially
Double
here.
bond is two sigma bonds. Right. Can everyone please stop talking, just because the people on Zoom are gonna hear, there's microphones all over the room, so if you're talking, they can't hear me, they can hear you. Or they can hear the two of us talking. Gosh, I hate having to do that, but yeah. Okay, what question was it?
It was question 30.
I think Brian had one question about the other one. So Brian said, you said that double bonds are composed of 2 sigma bonds, but that's not true. Double bond is composed of a sigma bond and 1 pi bond. That's what gives its double bond characteristic. And then a triple bond is composed of 1 sigma bond and 2 pi bonds to add up to a total of 3 bonds, triple bond, right? So whether it's a single, double, or triple, either of them or all of them only have 1 sigma bond, okay? And then we have question 30 by Rami's request. So iridium, we find iridium. And you might be lucky on the test if you get a question like this and he gives you the element symbol. You might be lucky if he does. So let's assume that he doesn't. And we have to look for iridium on the periodic table. So in this problem, I did give you the symbol, so you would be able to find IR. But again, you might not be given the symbol for. And we said that the valence electrons are the previous S electrons plus everything in the D subshell, right? So let's just do I guess let's just do something like manganese or, yeah, let's do manganese. You would count everything in the previous S subshell, so 1, 2, 3, 4, 5, 6, 7. Manganese would have 7 valence electrons. Iridium, on the other hand, you would count from everything from the previous S. Do 1, 2, 3, 4, 5, 6, 7, 8, and 9. So iridium would have 9 valence electrons.
Is there a reason that we don't take any, like, we don't count the ones in the F subshell? That's like
Because
in this,
it's not, for iridium, it's not filled till after. Well.
because the F subshell will be built
The F subshell is 3F or 4F,
for F.
so it's not gonna be your valence electron. It's not the outermost.
Okay.
It's all the way in the core.
It's, okay.
Yeah.
All right, thank you.
So does it already kind of show you at the very top the amount of valence electrons, or if you just counted them?
So for main group elements, yes. Main group elements are these, everything that's not a transition metal. So these are main groups. These are main groups. So like for nitrogen, for example, you can't, it's horrible quality, but it would say group 5A. So 1, 2, 3, 4, 5. Nitrogen has 5 valence electrons.
So was it just coincidence that you got around 9 valence electrons at IR, even though it's at the top, it says 9?
Oh, maybe. Oh, I guess so, yeah. Yeah, that sounds, you're talking about these numbers, yeah.
Yeah.
I see what you mean. I guess so. If it numbers it just like that, it would be the number at the top.
Is it always the case like that though?
I mean, the groups are still numbered 1, 2, 3, 4, 5, 6, 7, 8, 9. So I guess, yeah.
What I would find is 1, 2, 3, 4, 5, 6. I guess because that like that group 3. They never occupied.
Well,
Because the B block has 10, but on that row, it looks like it's just only 9.
well, lanthanum and actinium are actually supposed to be right here.
Oh,
It just shows because the F block can only hold 14 electrons. If you count each thing here, we have 15 here. So lanthanum and actinium should be right here. It's just they put them right here on the periodic table sometimes because they're called the lanthanide series and the actinide series. So let's see, what was someone's, I think there was another question, or were you saying, I know you were just talking to me, but was there anything else you had?
No, those are
Okay. You might be asked, there's some exceptions like molybdenum. We know that one of these electrons actually pops up into that orbital. So you might be asked something like, how many outer electrons does molybdenum have? Not valence electrons, outer electrons. And you would say, if you know the exception, that it only has 1 electron in its S subshell, so it would only have 1 outer electron. So just know your exceptions like copper, silver, yeah. All right, so chromium, molybdenum all have the configuration of NS1, and then it'd be N-1 D5.
then go with tungsten.
No. It's chromium, molybdenum, and then for copper, it is. For copper, silver, and gold, it's NS1, N-1, D10. So that's for copper, silver, gold, and only chromium and molybdenum apply for those other exceptions, the ones we talked about before.
Are there any other exceptions?
So the electron configuration.
Yeah, because I've been hearing like,
15 exceptions.
Yeah.
I've heard 15, I've heard 10.
Maybe 15 like total exceptions, like the ionization energy exceptions, electron affinity, all those things. But in terms of electron configuration,
I think that was.
it's just. All
What
right.
questions would they ask us over expanded electron affinity and ionization energy?
Are you talking about?
Probably something about like which atom is going to have greater first ionization energy.
Yeah, that's just like.
Yeah,
where
but
they
it-
end up, really, like you say, electron.
it's about just the first atom, like where it lies, because you know ionization energy increases from left to right and decreases as you go down.
So
But there's
F
something
has
that-
the greatest.
Weird.
F has the greatest fluorine.
Probably helium.
But that helium.
That's the whole class.
It's a noble gas, but you can still remove an electron. It's just so hard to do it. Because it's so stable. It's like trying to remove. I don't know. what I was gonna say.
Can we run through the periodic trends? Specifically, specifically the exceptions.
Sure.
So when you're.
Ionization, affinity. Radius as well, radius is there. And everything else. Yes.
Okay, I'll let Rich go through this table. I'm gonna get some water, if that's cool with y'all.
My TA is dehydrated.
I've been talking all day longer.
All right, electron configuration / periodic trends. So there are some exceptions, as you all know, to electron configuration. Those being chromium,
Oh, we just went over that, Rich.
molybdenum, copper, silver, and gold.
We're over here, man. Periodic trends.
So to reiterate, those exceptions are there. Then shielding exists as well. Periodic trends. So, all right, atomic radius. Atomic radius, basically, like to sum it up, it's the size of an atom, how big an atom is. And it decreases from the left to the right. Anybody know why?
Because as the shell goes up, it pulls it closer to it.
So what are there more of in the nucleus? Yeah, there are more protons, which what attract the electrons closer together, right? But there's a word for that. Or 3 words, I should say.
Up there. Ionization.
CEFF. A symbol called effective nuclear charge.
Yeah.
That
But
doesn't ring any bell.
atomic radius decreases from left to right due to increasing nuclear charge. That's basically what Eamon said, is where like there's more protons in the nucleus, so that pulls in all of the
Like a magnet.
electrons. Yeah, exactly.
I didn't do well in physics, but I know what a magnet.
But yeah.
So it also increases as you go down the periodic table. Reason being, there's more energy levels. And because there's more energy levels, there are more inner electrons as well, which increases shielding. Anybody know what shielding is?
Never got taught that.
The inner electron shells.
So the shielding is basically electron repulsion. You can have shielding from electrons in the same energy level and electrons in different energy levels. So what I mean by that is, for example, whatever protons, neutrons, whatever. And there are electrons here. So there could be electrons in this energy level, and there can be electrons in this energy level. So shielding can occur between these 2 red electrons, but it can also occur between the red electron and the blue electron. So, yeah, that's basically atomic radius. So sum it up, it increases down periodic table and to the left. All right, ionization energy. Ionization energy, to sum it up, is the energy required to remove an electron from an atom. So it is endothermic. What does that mean about delta H? It's endothermic. It's positive. And something about that, it increases from left to right due to, again, effective nuclear charge. Y'all know what that is at this point. And therefore, because of the increasing effective nuclear charge, it pulls even harder, so the radius will decrease because of the fact that it pulls harder. We know that the atomic radius decreases from left to right. And there's also this little equation right here, the electrical force. It's basically the electrical force between any two things is directly proportional to the charge between them and inversely proportional to the distance between the two charges. Possibly, yeah. I don't think you'll have to do any calculations on it, but like know how to apply
Just
it.
understand the concept behind
Then ionization energy decreases from top to or it decreases as you go down because again, the effective nuclear charge, or sorry, it decreases from the bottom to the top. So basically the radius will go up at that point, the force decreases and it's easier to remove. So the ionization energy, basically what you need to know, increases up and to the right. So it's easier to remove an electron from a thing with a large atomic radius than it is with a small atomic radius. Like, think about it this way. You have a running back with a football, right? I don't think an average person can stop that guy from letting go of that football. That's basically what a thing with a higher ionization energy is. It's harder to remove that electron from an atom. Like, say, for example, I was holding out this pen right here and not putting too much force on it. A lot of you could very well just come up and snatch this pen from me. That's something with a low ionization energy. It's very easy to remove that electron. All right. Now, there are some exceptions with ionization energy. There's, group 2 versus group 3. So group 3, it's easier to remove an electron from the p subshell as it is from a full s subshell, because the s subshell is already full and the p subshell is empty, or not empty, I should say, but only has like a couple electrons in it. So it's easier to pull from there than it is from s. So basically, it's easier to remove an electron from a higher like atomic orbital, I should say. So like it's harder, it's easier to remove an electron from a d orbital than it is from a p orbital than it is from an s orbital. And then it's the same thing here, like group 5 versus group 6. So group 5 versus group 6, it's easier to remove an electron from a pair of electrons. So it's easier to move an electron together, or it's easier to remove an electron when they're together than when they're apart. Because again, of the electron-electron repulsion, those two electrons don't want to be close together. So basically, summarize, group 3 is lower than group 2 for ionization energy, and group 6 is lower than group 5. So 2 greater than 3, 5 greater than 6. So I got 2 is greater than 3, 5 greater than 6.
You'll probably be tested on the exceptions, because Dr. Armand loves to test students on the exceptions.
Yeah. Because remember
Not the
that,
highest energy.
yeah,
Wait, what?
Saying when pulling out an electron, it's usually the highest energy. Like the highest orbital.
Oh, yeah, you're always
But
gonna
with
pull
this
from
one, it's gonna be
the P or the S, yeah.
yeah, it's because like the p electrons are like considered your valence electrons, so a lot easier.
They're further out from the nucleus than the S electrons.
So yeah, that's ionization energy. Electron affinity is the complete opposite of ionization energy. If ionization energy is the energy required to remove an electron from an atom, then what is electron affinity? Yes, the energy required to add an electron from an atom. Or to be more specific, it's the amount of energy released from adding an electron. And this is exothermic, because it's literally the reverse of ionization energy. And it follows the same trends as ionization energy, as it increases from left to right, and it decreases from the top to bottom, because again, of your effective nuclear charge. More energy is released when you add an electron from left to right, and it decreases at the bottom, because at that point it has a large radius, it can't hold that many electrons, so it just wants to get rid of a couple. And unfortunately for you, there are also exceptions for electron affinity. So if we look at group 1 and group 2, it's easier to add an electron to an S subshell as it is to a P subshell, because you're literally increasing an energy level at that point. And then group 4 and group 5, it's easier to add something to an empty p orbital than stuff that already contains electron, like an electron repulsion can happen again. And we don't like those. We don't want those. So sum it up. 1 has a greater electron affinity than 2, and 4 has a greater electron affinity than 5.
The second exception for ionization.
5 is greater than 6.
Any questions?
Alright. Okay. Now I see that one trend is missing from this list. And that is the trend of electronegativity. Electronegativity. So what is electronegativity? All right.
Doesn't involve the set.
I'm about to add a series of confusing words, but once I do, you'll understand what it means. So I'm gonna write down the word sucking power, because that is, so basically what it is electronegativity is, it's like electron affinity, but sort of different. It's the ability for an atom to pull electrons closer to itself. So ability for electrons to pull, or atom to pull electrons closer to themselves. Yes. That's why it's pulled.
Electronegativity.
Yes. Oh, and Eamon brought up another good point. Electronegativity determines polarity. So if something is very electronegative, it's most likely polar. The bond with that element is most likely polar. But if something's not very electronegative, it's not that polar. It's not polar, as they say. So electronegativity increases up to the right.
Increases or decreases?
Increases.
Yeah. If you forget, just remember fluorine is the most electronegative atom. Therefore, if you go closer to fluorine, electronegativity is going to increase. So whether it's going from bottom to top or left to right, it increases. If you're getting close to fluorine, you're getting more electronegative.
Fluorine has the greatest electronegativity of anything, as Bill indicated. Electronegativity value for fluorine is like my GPA 4.0.
Oh,
You know, that's just like.
The electronegativity value for fluorine is, but yeah, fluorine has the greatest electronegativity. And something else to note, noble gases do not have electronegativity because they're already stable. What's the point in attracting more electrons if you're already stable? So, but there are 2 exceptions to this rule. Anybody remember the 2 exceptions? We said it before. Well, that's all right. Xenon, that's one of them. And then what's the other one? Think of Superman.
Krypton.
Krypton. Xenon, Krypton are the only noble gases with electronegativity. That too is not even that much. Like, it's a very small amount. Yeah.
Is there a cap to how many, this is like not even regarding this, but is there a cap to how many electron pairs can be with xenon and krypton? Because I know, for example, xenon can have up to like 6 or 8.
Yeah. Remember that if it's like below phosphorus, it can have an expanded octet. So generally it's like 6 electron pairs. Yeah. Or the max any atom can ever have is like 12 electrons. 12 valence electrons.
And will he be giving us a electronegativity chart by chance?
Not really. He will not be.
Expected to memorize every electronegativity value. He may give it to you if it's required. That's what he did for our exam.
Okay, thank you.
Boron's like 3.0, but it's supposed to be higher according to the trend.
Yeah, just follow your trends, like the little. It's like the little thing from Fruit Loops, the follow your nose, follow the trends. Yeah, the little toucan thing,
Oh, yeah.
follow your nose.
Damn, Robertson, that toucan.
The rabbit was better.
Any questions about what we've gone over today? You'll have 2 more minutes.
Dipoles?
It looks like it's-
Okay. You mean polar ball? HF. So this kind of goes like with electronegativity. So which has a higher electronegativity? Hydrogen or fluorine? Fluorine. So the thing with dipoles is the dipole is always going to point towards the more electronegative atom. So in this case, it starts over the hydrogen and the fluorine is going to sort of steal, or as I've stated, suck all those electrons toward itself.
We're doing like an NH3, dipole movements are to the end.
Yeah, let's do carbon tetrafluoride. So let's see.
Yeah.
All right. Now for this molecule, is it polar or not? Non-polar. Why is it non-polar?
Because every end is pulling in this, each end is sucking the same.
Yeah, you think about it. Right?
The exact same molecule.
Yes. Exact same from all angles. So basically, every single dipole you have,
All around.
it's equally
Just all around.
pulling in the same direction. So everything is canceling out.
Okay.
Now let's do fluoroform. Now let's do chloroform, because y'all know that better. This is structure of fluoroform, by the way. So if you're ever gonna, make someone pass out, that's the structure for that.
Just, okay,
Yeah,
I'm gonna grab
make it
3 chlorine atoms.
Just put it together like that.
All right, good. My point being, is this compound polar or non-polar?
All gonna be polar.
Why is it?
Because the electronegativity difference is greater than 0.5.
How do you know the electronegativity difference?
Says hydrogen's all the way over there, chlorine's all the way over here.
They're so far away.
Or you can just look at it, the electrons are unevenly distributed within the molecule.
Yeah, you could also say that. So there's a dipole here, that cancels out. But there's a dipole here and a dipole right here. So there's a net dipole pointing this way. So you can say the molecule is polar because all the electrons are sort of concentrated around this fluorine. Sorry, Colin. That's where they're going.
Lone pairs don't affect that. Sorry,
I didn't see the page.
So let's say we had,
It affects the repulsion, but not the action. Like, it doesn't have its own dipole.
yeah. Yeah, lone pairs don't have their own. Say we have something like water. Why is water polar?
Repulsion of those electrons.
Because of the repulsion.
Because oxygen likes the electrons.
So it's gonna what? It's gonna what?
It's gonna pull it towards.
What do you mean by pull?
The dipole pointed to
The best way I can explain it is that its shell is not full.
It's sucking them in, right?
Yeah, and so
polar. It's a strong suck.
it's sucking.
It is.
All right, but my point being, so hydrogen, oxygen, there's a dipole this way, they both cancel out. However, the lone pairs right here sort of affect the polarity as they decrease the bond angle because those lone pairs really don't want to be next to each other. They're trying to be as far away from each other as possible. So that'll sort of affect molecules polarity, because they'll be, so those lone pairs will basically be like pulling in opposite directions.
What about K krypton dibromide?
Alright, so draw out the Lewis structure for krypton dibromide. Alright, let's do a quick Lewis structure review. What's the first step for Lewis structures?
One essential energy,
Before that,
the total valence electron.
all of those electrons. So bromine has 7, so 7 times 2 is 14, and krypton has 8. So 14 plus 8 is how much? 22 valence electrons. Now, as some people have stated, the central atom. What's gonna be our central atom?
Krypton.
Krypton. And then there's a bromine here and a bromine here. So now what's next?
Bonds.
Yeah, so we're gonna draw a bond here, and a bond here. So that's how many electrons do we use up?
4.
4, because there's 2 electrons in a bond. So 18 valence electrons. Where do the rest go?
Not low, but. So on
Yeah, let's go.
First you do the outer,
Yeah, the outer terminal atom, basically. So 1, 2, 3, 4, 5, 6, that's like 12 total. So there's 6 left. Where do the other 4 go?
On Krypton, because it can do it.
1, 2,
the
3.
central atom.
There's 2 left.
That one was.
I can add 1 more pair. Are you sure?
No, you can't, 'cause it's not as.
No, that's me.
Krypton does have expanded octet. Krypton actually does have an expanded octet.
But that's not.
It's under row 3.
It's under. Krypton and
It's
Xenon.
only the things under row 3, because I've been told that it's only like that group of 9. And
Yeah,
that's
and
it.
it's like.
No, it's anything
under row 3 can. Wait, hold on.
And row 3 itself too.
Row 3, not row 3.
So a second. Let's take a second.
This man, John.
Wait, was it everything under row 3?
Everything in row 3 and under.
All right,
Have an expanded octet.
so then you can subtract 2 more again, and then add another lone pair here. All right, now what I was trying to get to, is this molecule polar or non-polar? All right, we got some non-polar, we got some polar.
Polar. That's polar. How, if it's. If that's
Oh,
too many electrons
It's
on
symmetrical.
Krypton.
It's symmetrical, but-
How many of y'all say polar? Raise your hand. How many say non-polar? Right, polar, non-polar. Correct answer. What's the molecular geometry?
Linear.
Linear, yeah.
But
Electron.
so, if the electrons are considered linear,
It's non-polar.
Is this true?
it is indeed.
Is it because, so it's like, there's the actual molecule with like bromine this way. All the ones that have this.
It's like,
So it's like.
basically, everything's at a 180 degree.
So this thing here, if the terminal atoms are the same, everything that's highlighted yellow is gonna be nonpolar, as stated in the upper
That's
right.
what the highlights.
So as we see, what we're dealing with is this one right here, the very bottom right.
No, it's 5.
It's hard.
Bro, the first time you showed me this, I highlighted it without.
Okay,
We're dealing with this.
we're dealing with like that one, because you see that if it has the same terminal atoms, which it does, they're both bromine, it's gonna be nonpolar. Again, that's just a memorization thing. Hate to say it, but yeah. And Brian said he wants to see the exceptions again, so what I'm gonna do is just send this, I'll send this out to y'all. And y'all can do your thing for the next few hours.
All right, good luck on the exam. It's gonna be the last one of the year for the final.
Y'all gonna have to review sessions for the final, or do you lead against them?
Everything below, either maybe, no, it would be like.
Thank you guys again.
All right.
You guys have
So
a
you
good
can finish your
one.
chemistry.
Appreciate it.
Well, that's what I'm gonna do. You know,
Catch you in the library. I gotta go meet my class.
Two.
Two. How many people know?
Glad to do that like now.
So easy.
I'm in. Yesterday? No, 2:10. I was